Hey everyone, in this video we're going to go over a set of problems known as difference equations, and they pop up in a whole bunch of different areas in physics, statistics, etc. Before I start talking about what they are, it's probably worth mentioning their better known cousins, differential equations. If you're already pretty solid on what differential equations are, you can skip over to the next timestamp. So if we have two continuous variables, let's say x and y, and continuous meaning they can take on any possible value in the range we specify. So it could be like the range 0 to 1. X can take on any possible numerical values like 0.4, 0.00001, 0.1 recurring, or as a fraction 1/9. So yeah, there's no restrictions on the values you can take besides the limits we set it. And we also don't need to set limits. It could be the entire real number line. And if we know some relationship between them, we can work out derivatives. And derivatives tell us the rate at which one of these variables change with respect to the other. So dy dx tells us how quickly or slowly y changes with respect to x. And when we're able to relate these derivatives to one or more variables, we get a differential equation. Physicists eat and breathe differential equations. So examples of differential equations, I can make one up right now. Dy dx equals the value of x plus the value of y. Newton's second law, F equals ma, well, that's a differential equation. F equals mass times acceleration, which is the second derivative of displacement with respect to time. Schrodinger's equation, that's a famous differential equation, which describes how a slow-moving, well, I say slow as in like not relativistic, quantum mechanical particle behaves in some potential u, got a psi there, with some given energy. So it relates a spatial derivative to this time derivative I'm trying to squeeze in here. So yeah, that's the space derivative, that's the time derivative. Another example of a differential equation would be Maxwell's equation. So there are 4 equations, all of which are differential equations. And if you've seen my video series on them, you should be fairly familiar with where they come from. Not going to list them all out, but you get the idea. So I won't go into detail on how to solve these differential equations in this video. There's plenty of resources on that online. What I do want to consider is what happens if the variables we're differentiating over are no longer continuous. What if they're discrete variables, for example? What if they have to be like natural numbers? So the natural numbers are basically counting numbers. They're a set of numbers starting at 1, going 2, 3, 4, 5, and so on, just in better handwriting. Let's consider what a derivative would look like in this case. So say we have some function fx that takes in some x and spits out some natural number. So mathematically we'd say it takes in something from n and spits out something else in n. In the continuous case, we know that our derivative is defined by the limit as some variable h goes to 0 of f of x plus h minus f of x over h. And graphically, this just looks like, so you have some function, you have a point over here and another point over here, and separated by h apart. And what we want to do is we want to let h get really, really tiny. So along the x-axis, this second point looks much, much closer to the first point. And we want to look at the ratio of their vertical and horizontal separations to get the derivative. So this is basically the slope or the gradient. In the discrete case, however, our functions look a bit different. They're not smooth curves anymore. So I'll label both of these f, both of these axes. In the discrete case, our x-axis is separated into these blocks with no numbers in between. and our value f could be this much, so it could be equal to 1 for when x is 1, it could be equal to 2 when x is 2, it could be 1 again when x is 3, it could be 3 when x is 4, it could be 4 when x is 5, and what you'll notice is there isn't any continuous smooth curve. It's like a bunch of discrete jumps with vertical and horizontal lines. So the closest we can get 2 points to each other without them both being the same point is 1. So if we plug this same idea into this definition of a derivative by just setting h as 1, we get the discrete version of derivatives. We'll just say this discrete version of derivatives is equal to f of x plus h, which is 1 now, minus f of x divided by h, which is 1. And this is just the difference between two successive f values. And that's what the discrete version of a derivative is. It's just the difference between two consecutive x values. And this difference is guaranteed to be a whole number because this over here is a natural counting number, and this over here is a natural counting number, and they must be a finite set of blocks away from each other vertically as well. So that you can't have like this being 4.5, this has to be whole natural numbers. And similarly, we can take the second derivative in our discrete world, which is just the, so if I let f prime, this is a bit of abusive notation, equal the derivative, the difference, our second order derivative in discrete space is just the derivative of the first derivative, and that's equal to plus 1 minus f prime x plus 1. So that's so we've just expanded this out into these two terms, and if we do the same for the other one, that would be, well, the first difference of x would be f of x plus 1 minus f of x, and this tells us that that's equal to f of x plus 2 minus 2 f of x plus 1 plus f of x, and that's our second order difference, which is the discrete version of a second order derivative. Now we can relate these differences together in what we call difference equations, and we solve them in a really similar way to how we solve differential equations. So let's look at an example. Say we have the difference equation that says f of x plus 1 is equal to 4 f of x minus 5 f of x minus 1. Notice how this involves a value of x, f at the value of x, and the value of f before and after it. So it involves the differences between, well, it involves two differences. So it's called a second order difference equation, because second order differences take 3 x's into account, whereas first order differences only take 2. Cool. So to solve this, we will do a very similar method to the method of undetermined coefficients from differential equations. So we'll try a dummy solution, which instead of the exponential e to the whatever in our continuous differential world, in this case, we'll go for a different kind of exponential. We'll say, let's try f equals some variable lambda to the power x. In this case, we can plug this in to our difference equation, and we'll get lambda to the x plus 1 equals 4 lambda to the x minus 5 lambda to the x minus 1. Let's divide this throughout by lambda, and we'll get lambda equals 4. We'll divide throughout by lambda to the x, sorry. We'll get lambda equals 4 minus 5 over lambda, and this is just a quadratic equation, which we can see more clearly if we just rearrange it like this. 5 equals 0. Cool. Now we can use our trusty quadratic formula to solve this, and we can see this is equal to minus b plus or minus the square root of b squared minus 4ac the whole divided by 2a, which evaluates to 2 plus or minus square root of minus 1. So we've got complex roots, and I know this seems like a really far jump out. We're now in the complex plane, and we started off with natural numbers, but trust me, we'll get there. So this gives us two solutions, two linearly independent solutions actually. So we have this first one that's equal to, we know what lambda is now, to the power x, and the second one, which is lambda to the power x. So our general solution, just like in differential equations, would be some kind of linear combination of this. So we'll say this is equal to c1, some coefficient, times this, plus c2, some other coefficient, is this, where c1 and c2 are some complex numbers. Sweet. So this is our general solution to the difference equation, and it looks kind of nasty. So let's say that we've been given some kind of boundary conditions to solve this difference equation, and in this case our boundary condition is f0 and f1 are both equal to 2. So let's plug this into our general solution. So our first boundary condition says that f of 0 is 2. So f of 0 would be c1 times 2 plus I to the 0 plus c2 times 2 minus I to the 0, and that's equal to 2. So this tells us that c1 plus c2 must equal 2. So plugging in the second condition, f of 1, we get c1 times 2 plus I to the power 1 plus c2 times 2 minus I to the power 1 is equal to 2. So now we've got this system of two linear equations to solve. Let's just solve it by substitution. Let's label these 1, and this equation 2. And from 1, we know that c2 can be expressed as 2 minus c1. Plug that into 2. We get c1 times 2 plus I plus 2 minus c1 times 2 minus I equals 2. Expand out the brackets. 2c1 plus I c1 plus, so that'll be 4 minus 2I minus 2c1 plus I c1, and all of that equals 2. Now, grouping together all the c1s and the constants, we get c1 times 2 plus I minus 2 plus I, 4 minus 2I equals 2. This boils down to 2I c1 is equal to minus 2 plus 2I. Divide both sides by 2I, we get c1 equals minus 2 plus 2I divided by 2I. We can times top and bottom by minus 2I. Complex conjugate of the denominator, and that's equal to 4I plus 4 divided by 4, which is 1 plus I. And we know from 1 that c2 is just 2 minus 1 plus I, which is 1 minus I. And ta-da! We've got what f is equal to. So f of x is strangely a complex function with c1 equaling 1 plus I times our first linearly independent solution to the power x plus c2, which is 1 minus I, times our second linearly independent solution. And that's our final answer. Fun fact, this difference equation over here that we just solved, its solutions are the Gaussian integers, which are equal to their own conjugates. And Gaussian integers are just complex numbers where complex numbers of the form a plus bi, where a and b are both integers. Thanks for watching.